let's calculate this definite integral here. The definite integral from 4 to 9 of ln y over the square root of y with respect to y. And before I even get started, I'm just going to write this in a way that might be easier for me to handle, and that is 1, take this square root on the bottom, change it to an exponent, which is y to the 1/2, and then I want to put it on the top by making a negative exponent. So this is y to the negative 1/2 ln y dy. So just a rewriting of the integrand. So now I have to ask myself what kind of what method should I use for integration here, and the idea would be I have one function times another function, so probably integration by parts, but I'm still not quite sure. But if I notice here I have a logarithm of y, if I take its derivative I'd have a 1 over y, and integration by parts lets me take a derivative like that, so the 1 over y would actually make my life much easier. So yeah, let's go ahead and try integration by parts. Specifically, we're going to let this be u, because when I differentiate it, it becomes 1 over y, and I'm going to let this be dv by dy. So now I go and I fill in all the pieces that I need for integration by parts. U is ln y, du by dy is equal to 1 over y. V, don't know yet, but I do know that dv by dy is equal to y to the negative 1/2. And if I anti-differentiate this, I'll be able to get what v is, which means it is 2y to the 1/2. And I can double check this. If I differentiate this, the 1/2 will come down, and 2 times 1/2 is just 1. And then I'll subtract 1 from the exponent, and it becomes y to the negative 1/2. So this now allows me to use the integration by parts formula. So u times v, so 2y to the 1/2 times u is ln y. Of course, I'm still evaluating from 4 until 9, and the rest of the formula says I still need to integrate from 4 until 9. V, which is this, 2y to the 1/2 times du by dy, which is 1 over y, dy. I'll just separate this to make sure. That becomes 2y to the 1/2 ln y, still evaluated from 4 to 9. And now I have this integration here. This 2 is a constant, so it can come out front, 4 to 9. And y to the 1/2 divided by y is y to the negative 1/2 dy. Okay. So I'm just going to keep copying this down until I want to deal with it, which I don't quite yet, from 4 until 9. Now I can do this anti-differentiation. This becomes 2y to the 1/2. I can check that again. If I take this derivative, I end up with y to the negative 1/2, so this looks like the right antiderivative, but of course I have to evaluate from 4 until 9. And so now I can go in and actually evaluate these things. So the first part, I'm going to substitute in my 9, so I get 2 times 9 to the 1/2, logarithm of 9, minus what I get when I plug in 4, 2 times 4 to the 1/2 times the logarithm of 4. So that's the first part, minus 2, and now let's do the second part, 2 times 9 to the 1/2 minus 2 times 4 to the 1/2. Okay, and now I can simplify this up a little bit. 9 to the 1/2, the square root of 9 is 3, so this becomes 2 times 3, which is 6. This 9 actually becomes 3 squared, so I have 3 squared in there instead of 9, minus 4 to the 1/2 is 2, so square root of 4 is 2, times 2 is 4, and then times the logarithm of this 4 becomes 2 squared. Okay, and I'll just rewrite that 2 squared. Here we have minus. I'm still going to just have that minus 2 sticking out front. I'm going to deal with inside the brackets. 9 to the power of 1/2. That's the square root of 9. That's 3. 3 times 2 is 6. Minus square root of 4 is 2. 2 times 2 is 4. So this becomes 6 minus 4. And now I can simplify this by taking the 2, bringing it all the way down out front. This becomes 12 ln 3 minus, this 2 can come out front as well, 8 ln 2, and minus 2 times what's in here, 2. So this is minus 4. And this is the final solution.